Come back. So now we start on section 1.5 of chapter 1. Chapter 1, Functions and Limits. Section 1.5 covers the limit of a function. The limit of a function. To find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. Let's investigate the behavior of the function fx equals x squared minus x plus 2. For values of x near to, now that's important, near to. We are not equal to 2, we are near to. So what happens to values of x near to? Here is a table. So you see x values, they have used 1.0, 1.5, 1.8, 1.9. Notice they are getting closer to 2, but they are not equal to 2. Likewise, here is 3, 2.5, 2.2, 2.1, 2.05, so on. It's getting closer to 2, but it is not equal to. All right. If you want to draw a picture, here is a good option. Let's see. Say this is your number line. All right. So somewhere here is 2. Somewhere to the right of 2 is 3. Somewhere to the left of 2 is 1. So what are we doing in this particular table? X values start at 1, then go to 1.5, then go to 1.8, 1.9, 1.95, 1.99, so on. So it's getting closer and closer to 2. So what are we doing in the first table here? X value is approaching 2 from the left. This is 2. You're approaching 2 from the left. The second table, you're starting x equals 3. Then you're moving to 2.5, then 2.2, 2.1, 2.05. That is, x value is approaching 2 from the right. All right. So 2 is here. One table is investigating what happens to fx as x approaches 2 from the left. The other table investigates what happens to fx when x approaches 2 from the right. Look at the values. All right. X is 1, you have fx equals 2, and so on and so forth. So what was this fx? Don't forget, this fx is here. Fx is x squared minus x plus 2, right? Okay, so this is what we want to investigate. So what have they done? They have taken different x values and found the corresponding fx value. So when x is 1, they have plugged it into fx. 1 minus 1 plus 2, 2. And so on. For different values of x, they have calculated fx. Likewise, when x is 3 onwards, coming from the right, they have calculated different values for these different x values. X values, they have found the fx values. When you see the table, notice the numbers, values here, 2, 2.75, 3. So you're increasing. You're increasing, but you're not going beyond 4. In fact, looks like you're getting close to 4. Likewise, from the right hand side, you start at 8 and you're decreasing. You're decreasing, but somehow you are unable to cross 4. So you're approaching 4. Here you're approaching 4. So what's happening is, if you can imagine the picture, the picture is possibly for 2, the value is going to be 4. That is, the height is going to be 4, it seems. From the left, you're increasing. Oops. From the left, you're increasing towards 4. From the right, wherever you are, okay, I can't draw there, but wherever you are, you're decreasing towards 4, basically. That's what is happening, okay? So, let's see the actual picture. So that's the parabola, right? A second degree function is going to be a parabola. So somewhere is here 2. As x approaches 2 from the left, the value of f increases to height 4. As x approaches 2 from the right, the value of f decreases to 4. Okay, we could have actually plugged in 2 here, but I'm not interested in value at 2. I'm interested what happens near 2. So a picture helps us understand this better. Okay, it appears that we can make values of fx as close as we like to 4 by taking x sufficiently close to 2. We express this by saying the limit of the function fx as x approaches 2 is equal to 4. So notice this is an entire sentence. The limit of the function fx as x approaches 2 is equal to 4. So instead of writing all of this, you have a quick way of writing lim as x approaches 2 of fx, that is x squared minus x plus 2, is equal to 4. So notice mathematics is simply a way of writing in short form of a long sentence. So when you see lim x approaching 2, that's what this is, the limit of as x approaches 2. That's this part. Of the function this, of is usually represented by parenthesis. So of whatever your function is equal to, you know the notation for is equal to, it's just these 2 lines, and 4 is 4. All right. In math mode, what you do is you start math mode \lim. You see lim, and you have a space underneath x2. 2 is that arrow 2 of fx. What was my x squared minus x? I forgot. Plus 2. All of this is 4. Okay, that's how you would write in matcha. So here is the intuitive definition of a limit. Suppose fx is defined when x is near number a. So you are worrying about being near a. F is defined on some open interval that contains a, except possibly at a itself. Then we write limit x approaching a, fx is L. Limit of fx as x approaches a equals L. If we can make the values of fx arbitrarily close to L, restricting x to be sufficiently close to a on either side, but not equal a. We are not worried about being equal a. Okay? This says that the values of fx approach L as x approaches a. In other words, the values of fx tend to get closer and closer to the number L as x gets closer and closer to the number a. From either side of a, but x not equal to a. Okay, I'll stop my video recording now so that the video doesn't get too long. Okay, continue until next one.